So now that we have a good overview of how to calculate electric potential and essentially what electric potential is, it's a good time to talk about the differences between electric potential and electrostatic potential energy, because they're related, but they are different. So I'll first pose a question. Are electric potential, represented by Vp, and electrostatic potential energy, represented by U, the same? So hopefully you've realized that they're different letters to represent different things, which means no, they are not the same. And the analogy I want to use is one that you're familiar with and that we talked about in the introductory part of this chapter. We have gravitational potential energy, we have gravitational potential at a point in the gravitational field. And that gravitational potential is the gravitational potential energy of a unit mass placed at that point. So similarly, the electric potential at any point in the electric field is the electric potential energy of a unit positive charge at that point. So very similar to gravitational potential versus gravitational potential energy, when we talk about the electric potential energy, it's going to be a certain measurement of stored energy, and then when you divide it by the unit positive charge, you get the electric potential. So a few key things. Electric potential is the amount of work done to bring your test charge Q from infinity to a certain point P. Meanwhile, the electric potential energy is the energy needed to move a charge against the electric field. So that's just an overview of the differences between electric potential and electrostatic potential energy. We're now going to take a closer look using a few examples. So let's take a closer look. So I want to be able to look at a charge Q1 let's just redraw this as Q1. And let's say that this charge Q1 is already there, it's in existence. So Q1 alone, basically it has no force. Acting on it. And because there's no force acting on it, that means there's not going to be energy needed to move a charge against any electric field. So therefore, it has no stored energy. So then what happens if we bring another charge, let's say Q2, within the vicinity of Q1? So we're going to say that they are a distance r, 1, 2 apart, and this is at a point P. So Q2 at P will have an electric potential of something that we've determined before. We know it's going to be K Q1 over R 1, 2. So in other words, I can call this the work I have to do to bring a +1 coulomb charge to my point P. So what does this mean? This means that the work to bring Q2 to P is given by Q2 times Vp stored as potential energy. So you can verify that through the previous sub-chapters that we've gone through in this chapter. So we know that the work is going to be Q2 times Vp. So basically the amount of charge times the electric potential. Now that we have that, that means we'll be able to calculate the electric potential energy. So then, therefore, delta UE is equal to Q times Vp, where Q is equal to the charge we are bringing in, and Vp is the electric potential at that point P. So then, looking at this example, once it is assembled, or once all the charges are where they have to be, the total stored energy of the system is going to be U total is equal to, remember, we have some stored energy from the first charge and some stored energy from a second charge. We know that the first one is 0, and we know that the second one is going to be delta UE. So I can say the initial energy of Q1 is 0, and therefore this is equal to Q Vp. So we've taken a look at what happens if we bring one charge into the vicinity of another charge. Now, what happens if we bring in a third charge? So there's going to be more that we have to consider. So we have to think about, if we bring in an additional charge to this already assembled system of two charges, what kind of things are going to change? Let's first draw this out. So we have Q1, and we have that Q2 from before, and let's say I have to bring in a Q3. That means I have several distances to consider now. I have R12, R13, and R2 acting upon 3. We can call this point P, and we can call this point P prime. So if we add a third charge, we know the energy stored is going to be, or the energy stored, let me rephrase that. If we add in the third charge, we know that the energy that's already stored in the system comes from Q1 and Q2. And we know that it's going to be K, Q1, Q2 over R12. The reason why it's K, Q1, Q2 is because, remember, we have UE equals to Q, which is the charge we bring in, times VP, and we define VP as K, Q1 over R12. So we brought in a Q2, and therefore we have K, Q1, Q2 over R12 for our existing energy. So then we already know the existing energy. Now we have to figure out the electric potential at point P prime. So the electric potential at P prime is going to be V equals to, there are two charges acting upon Q3. So you have K Q1 over R13 plus K Q2 over R23. So that's the total electric potential at point P prime. After that, we need to look at the change in potential energy. And that change in potential energy is delta UE. Is equal to Q3 VP. So similar as before, instead of QVP, we now have, we're bringing in charge Q3 with VP. And I know that this will be K Q1, so this would be VP, or VP prime. K Q1 Q3 divided by R13 plus K Q2 Q3 divided by R23. So now that we have the change in potential energy, we should probably figure out the total energy. So the total energy stored in the system will be this. We have the final energy stored. We have the initial energy, which we'll call UI, plus the new change in potential energy, and that's K Q1 Q2 over R12 plus K Q1 Q3 over R13 was K Q2 Q3 over R23. So we've calculated the total energy. Now, is it possible for us to state this for a general case? And it is possible. So for a general case of an nth number of charges, we have the total energy being equal to K, since it seems like we can factor out the K from each of these. It's going to be a summation from 1 to n, where we have Qi Qj divided by Rij. And so we have a summation of various different types of charges with as many charges as we want.